Okay, hello, welcome all. We will be studying multi-layer perceptron architecture today. So in this architecture, you can see the three portions of the multi-layer architecture. The first portion is the input layers. In the middle, we can have the hidden layers or the hidden nodes. And in the last layer, we have the output layers, or we can say the output neurons of a multi-layer perceptron neural network. So we can say there are neurons in the hidden layers and the output neurons, but there is no neurons in the input layers. So input layers are considered as the processing unit inputs. It can be labeled as xi, xi to xn, the inputs xn till xn, and in the middle layer there are the hidden nodes, and the hidden layers are being denoted as being as their suffixes. So if we move forward, we can see the XOR problem. The XOR problem is we know all about the Boolean XOR problem that cannot be solved using the perceptron neural network. So a single perceptron cannot solve a Boolean XOR function because it doesn't preserve the linear separability functionality in XOR. The linear separability functionality can be achieved with the help of multiple perceptron conjugated or connected with each other and producing the outcome of desired XOR function. So in this solution, we have used the activation function, which is denoted as sign function. In previous examples, you might have seen f or g as your activation function. So in this lecture, we are actually continuing with a phi, and in suffix v, where v stands for the transfer function, and it is denoted as a weighted sum of xi wi I equals to 0 to m, where when we denoted I from 0, that means it actually contains the bias in it. So we'll be as far we are moving on the on this portion. There are some three neurons in this picture we are seeing. One neuron is from here, where is x1 and x2 cap is being denoted. The x2 cap has a negative weight, inhibitory weight in his line, and the positive weight is in his line is being denoted as this way. Okay. um, okay, so and x2 and x1 bar is being denoted in this portion, and we know that in a XOR function, if x1 XOR x2, we can linearly produce as x1 x2 bar or x2 x1 bar. So this can be happened in this OR portion. This is actually denoting the OR notation, the OR circuit, and this is the AND NOT circuit, and the AND NOT circuit representation of x2 and x1 bar and x1 and x2 bar. So these are the input. The input not necessarily be shown in a square box. You can use a suffix of a circle also, but these neurons contains a bias. These are the bias of this neuron, and this is the bias of this neuron. And also see, there is some different biases can be considered in a different layers also. So the output layer consider only 0.1 bias. So, and the nodes might contain different kind of threshold as well. I think we are all acquainted with the concept of the thresholds, the biases, and also the weights assigned. The positive weights are being considered as excitatory, and the negative weights are considered as inhibitory. That will help us to trigger the notations in this way. And at this neuron, we are actually implementing x1 and x2 and end not x2, so that there is implementation of and not x2. So if you can see the linear separability line, this is a this portion, like x1 and x2 bar, this can be represented with a single line, single perceptron line, and it can be called as a perceptron. This only one node can be called as a perceptron, and this also can be called as a perceptron because this all can be operate linearly, separability, functionality in between the resultant result. But these two these two are not suffices to implement the XOR one, the XOR function. So therefore their results are combined with an OR function. With the help of that OR, where it can classify the XOR function properly, and for that they need to add a layer after the perceptron layer also. So that's why this layer becomes a hidden layer, and this becomes an output layer, and this becomes an input layer. And this architecture holds a multi-layer perceptron. So this architecture holds a multi-layer perceptron. In context of this layer is considered as a hidden layer for the XOR function. So we used step sign function for each neuron to get activated with a value after it's getting the result. So let's move forward. After solving the XOR problem, we are actually watching the next issue that we are going to address, that is called the sigmoid function. We used a sign function in the XOR one, but in the real world we need some nonlinearity in manner. That's why we used sigmoid function. So what sigmoid function actually does? Sigmoid function actually a function which is differentiable and which can support nonlinearity, and here also Vj, that means the transfer function, is provided as an input in the activation function, and mostly in the activation function, the activation function's derivative can produce the activation function by the activation function and its inverse activation function itself. So that is the one of the most powerful power of this activation function, this sigmoid activation function. And from here we can see there is an a is a constant here. So if we increase the a to infinity, this sigmoid function can turn into a threshold function. A threshold function can be turned into if a moves towards to infinity. So in the learning of multi-layer architecture, multi-layer perceptron, what learning algorithms should be used and what learning algorithm should we be proposed? Like when the calculation of the result is being calculated, there is a forward signals that is going from input to hidden layers and generating outputs in the output layer. This portion is called as feed forward or feed function signal, forward signal portions. So you can see in the green lines that the results are computing in the neurons and being forwarded with the green line to the output layer. And in the output layer there is a loss function. The loss function takes two inputs, the training value and the computed output value. And the training value and computed output value computes the error. So the error then repropagated with the red dots. You can see the repropagation from the output layer to the previous hidden layers, and thus the hidden layers also propagate that error to their previous layers. So this error with the red line, the error propagation, is being denoted as error signal. So there are two kind of signals, that is called a feed forwarding process, and another process is called the backward propagation of error. That error signal will be flow from the output layer to the input layer. So from input layer to output layer it's called feed forwarding, and from output layer to the input layer is called error signal flowing. And one is called forward propagation and another is backward propagation. So back propagation of that portion. So the back propagation is nothing but it adjusts the weights of the neural network in order to minimize the average square error. What it actually tries to minimize is actually tries to minimize the loss function. In this case, we have the loss function as mapped in average squared error. So we are using average squared error as a loss function, and our target to model or to train up our neural network so that it can minimize the loss function. So let's see how we can do this. So let's first look what is average squared error and how we can compute the average squared error of a signal of a loss function. So in the error signal of output neuron J, we are considering a particular neuron J at presentation of nth training example, that you have several training examples. So you are actually picking one of the training example, one of the nth training example, and that you can from that you can compute the average square error. How you can compute it? For the nth row, that for AND gate you have 4 rows, so let's consider a third row. So n equals to 3, so that's how n is computed. So for that nth row, the current output will be of the current error output of that neuron, J neuron, will be yj of n. That is computed. It is computed output from the neuron, computed output of the neuron, and dj is the desired training value that is being provided. So the difference of these two will be considered as an error. So error of jth unit, error of jth unit in the nth training data set will be desired training value minus the computed output of that neuron in the nth one. And then what we will do, we will try to average of full container outputs. Like in the output layer, if you have several output neurons, you need to perform those as an integrated way. So in that purpose, we are considering that you have C is a contour size. Contour size means it will have the number of neurons. C is a set where the number of neurons of the output layer coincides, and n is the training size that of the training set. So we are saying that the half has been coming from the formula, that is summation of each neuron error that belongs to the output layer C will be its own squared error that is computed in the previous example. So why we take the square error? Because if we take absolute error, if we take the original error, there's some error might be cancelled out in terms. Okay, so in that case we need to preserve the information of the error also. So for that we need the energy, and for that we actually squared the error, so we can preserve the error information and sum up the total error information and provided as a output layer of nth neurons in the domain. If you have only one neuron, then this summation won't become. So there will be only one error, and only the upper calculation will be propagated in the average square error part. And whatever the average learning performance, the measure of average learning performance, we will be trying to grab this result as all the training set. For all the training set we will computing the errors, and we will take the average of 1 by n of that error, so to get the average squared error error part. So our target, our primary goal for the neural network perspective is to adjust our weights of the neurons in such that we can minimize this average square error. So we can minimize the average square error so that our model can learn their training set accurately, more accurately. So that is our main goal. So let's jump upon some notations that might be helpful in some computations that we need to compute throughout the minimization process of the average square error. So our goal, we are fixed about our goal. So our goal is to minimize. So we will try to minimize the average square error, which is our loss function. So we need to adjust our neural networks weights in such a way so our loss function can be minimized. Okay, so let's denote in the output layer a neuron can generate an error. So that is being termed as EJ. That is a single neuron's error. Computed output passes through the loss function and generates EJ. Okay. And what about the YJ? YJ is nothing but the output of the neuron. So let's guess the basic differences. EJ is DJ minus YJ. Okay, so EJ is a single output error computed from jth neuron. Okay, and what about YJ? YJ is nothing about phi of VJ, where phi of dot becomes activation function and Vj is nothing but a transfer function. And you can see the transfer function is considered as induced local field of neuron J, and it is being formulated as Vj is formulated as summation of I equals to 0 till m, and the associated weight with Wji, and the incoming inputs are being considered as Yi. So because the output layer is being connected with the previous hidden layers, they are also neurons, they will generate Yi's. Yi's, that means they are generating phi of Vi. What is Vi? Vi means those neurons incoming transfer function. So these are incoming transfer function of those neurons, and phi is the activation function of ith layer, and the output of the ith layer will be Yi's, and Yi's will be try to connect it with the jth layer, which is considered as the output layer. So we can consider this as a ith layer, and these are in jth layer. So these are connected. These outputs are considered as Yi, and these outputs are considered as Yj. So I am actually trying to depict these things in the picture. So these are the main notational phases that we are actually carrying out. Some more notations will be like if you differentiate dyj with respect of dvj, then we will be considered as phi prime of vj, the activation functions derivative. So this is also considered as the activation functions derivative as well. So these are the norm things that we are actually going to cover. So why we need the derivatives? Let's see. Because we have already learned the Heb's learning rule. If you can recall, the Heb's learning rule was W nu equals to, if you have some old weights, you need to update that with the learning rate, multiply it with the incoming input, multiplied with the error. That error is being computed like the training value minus the computed output value. So that was how the error is being computed. So in the Heb's rule, this portion is being considered with the delta W. Okay, so update rule is based on the gradient descent method. Take a step in the direction yielding the maximum decrease of loss function. Maximum decrease of the loss function, that is, we are calling that if we can decrease the error, like the graph is being like that way. So if you are in this position, then the gradient will direct you to the next phase and you will move to the next phase from this one until your direction becomes in a flat position. We actually desire this position for making our error loss prone. So making our error loss prone, or we can say we reach the minima of a loss function, because from there we can say there will be no loss when the function will residing in this point. Okay, so we are actually trying to identify this point, and for that a partial derivative function would help us, or a gradient descent method will help us for achieving that part. So why we are taking a minus sign? Because step is in the direction opposite of the gradient. Normally the gradients are in upscale, so we are actually going to the down phases, so that's why the gradient is in a minus position. So what about WJI? The WJI is nothing but the associated weight link of I neuron to J neuron. Normally we actually saw from to in the forward passing part. This is considered as forward passing, feed forward passing from to. Here is also considered as from to, just a signal with the help of to from, that is being considered as for error pass. So for that we are actually computing the error pass. For that's why our I from neuron I, it is moving to neuron J. So basically if I is the neuron, is J is the neuron, and this is the associative weight of Wij is considered for forward pass, Wji is considered for error pass. So that is the main differences to understand this architecture as well. So why WGI? Because the value will be made the same, but the sign or signatory differences is being denoted as WJI. Okay. So the delta Ji is being represented as minus eta. This eta is being considered as a learning rate. We have been considered as LR, so we will be using a notation, and it is considered as a learning rate. LR means learning rate, and delta E is with respect of the E with respect of, we are taking the partial derivative of error function E with the respect of WJI. So WJI means the weight with the respect of weight. What can we define, or how can we define the delta E? So in this correspondence, let's dig down a little bit of more. So let's see this picture. How many neurons are in there? We can see there is only one neuron. Here it is the neuron. So this neuron contains three parts. We already know the transfer function part, the activation function part, and the output function part. From here what we can say, Vj is equals to summation of Wji multiplied by Yi. Okay, and for phi Vj we can consider it as our activation function, and we can say Yj is nothing but output of phi of Vj. Okay, so these terms are being considered here. So y minus 1, because in this point we can say it's dj minus yj, just multiplying it with the minus 1, and it is producing an error. So ej is nothing but dj minus yj. So the computed output, it is yj, the computed output. Okay, So far these equations are being clear for us, and we are considering only the output layer. This is being considered as only the output layer. So for the output layer, this is being considered as Ej equals Tj minus Yj. So let's dig down. This neuron can have a local induced error. So it can consider a local induced error. What could be the local induced error? We can denote it as it is in delta J format. This local induced error will be computed within this neuron, considering the errors that is being generated by the loss function and being propagated throughout the other neurons also. So this error, this term is only considered for the neuron by itself inside it. Okay, how? So what parameter or what can define a local induced error? So the local induced error is being defined in the optimization with respect of the incoming input. This is a partial derivative. So in this neuron, the input portion is Vj. So with the respect of Vj, how much loss this function can perform to the network, that is being computed with the partial derivative of the overall error based upon the incoming inputs it has. Okay, so that is being considered as the local induced error computed inside the neuron itself. So if the overall error, we know that half of Ej square, we are counting this as J in the output layer. So let's consider this as a chain rule. So let's consider the chain rule with respect of the figure we are having here. So let's consider del E by del Vj. We are not considering the minus sign yet now. So it can be rewritten as delta E is fully dependent upon small ej, right? Because the neuron is generating some error, then it can impact on the error function directly. And for the error function, this delta Ej is slightly dependent upon the output. Okay, and the output is dependent upon the incoming inputs. So all are in J's notation. Okay, so let's dig down with the last one, and for there, so we can rewritten this in using of calculus chain rule. So this can be rewritten in the chain rule as well. So what about delta Yj and delta Vj? We know that Yj is equal to phi of Vj. So if you differentiate with respect of Vj, then it will become phi prime of Vj. That is the portion of here. We are replacing that one. Delta Ej and delta Yj, if you considering this equation, Ej, so delta Ej by delta Yj will produce as a 0 and minus 1, which is leads to minus 1. So here in the middle portion we are having minus 1. And if you consider delta E by delta Ej, so if you consider half, if you break down the summation E1 square, E2 square till Ej square plus En square, only Ej will be remaining as a variable and others will become a constant. And we know that if others are constant, then delta E of delta Ej will become 0, 0, 0, half, 2 will come in front, Ej. Okay, Ej square will become Ej and half will be gone. That means only Ej will stands. So there is Ej will stands. So for that, look, if we replace the local induced error delta G, we can say minus 1 and minus 1 is going can cancel out. So we can say Ej by phi of Vj. So we can say the error being generated from the output neuron is multiplied with the activation function's change of rate of the activation function can produces the local induced error of the output layer. So it is being considered as local induced error of the output layer. Okay, so let's consider this equation in a more generic format. So as we have already seen that delta J is being considered with the incoming inputs of delta Vj with the respect of whole network being optimized with the incoming input of that neuron of J neuron, right? So the local gradient or local induced error computed inside the neuron is none or less the error of J and the activation function derivative. So the derivative, we can see the derivative in the format as well. So from there we can consider the delta J is delta E by delta Vj. In the weight update delta Ji, we have eta minus we have delta E and delta Wji. Okay, so the weights are being considered as errors. So for jth neuron, if we can rewrite this equation in terms of Vj will be chain ruled with weight because it is dependent upon the weight. So we can rewrite the equation eta minus will be considered in tangent. So delta J, that is been minus delta E by delta Vj. So we can rewrite these things, and whatever the Vj and Wji, as usual Vj is also a summation of I equal to 0 to Wji yi, right? So till m. So we can rewrite it, or if Vj is being differentiated with Wji, only yi will remain and the others will be cancelled out because those are considered as constant. Only Wji associated with yi will remain and other will be cancelled out. So we can say it yi. So the update rule of Wji can be rewritten as the learning rate multiplied with our local gradient or local induced error. We can say both the term is correct. Local induced error multiplied with the incoming inputs with the jth neuron. Okay, so far this equation can be reused for updating the rules of the output layer, where delta J of output layer, we know that its value is Ej phi prime of Vj. So let's consider the update rule. So how the update rules equation is come. So here it is being depicted, and for how delta Vj and delta Wji is considered as yi and this considered as delta J, and we can replace this, and how chain rule can be defined. Here it is being explained, clarified with clarity. So the compute of local gradient of neuron J can be classified in two categories. Like the key factor is to calculate how error of the output neuron can be considered, that is called Ej, and if J is output neuron, what will be happen, and if J is hidden neuron, what will be happen. So these two parts are being designed or being shown in the next periods. So if the output neuron, if J is an output neuron, there is a straight cut of calculation that output neuron will produces is output to the loss function. The loss function will provide him the error, and the error is being computed like Ej equals to Dj minus Yj, and after that it being provided for the local gradient of it being provided to compute the local gradient inside the neuron itself, and that is called delta J equals to Dj minus Yj. That is being this place being forwarded, and we already know that local computation of the output neuron is considered as phi prime of Vj. Okay, so let's move to the next one, that is called if the neuron is being hidden, how it will be computed. If the jth neuron is hidden neuron, then how it will be computed. The local gradient for neuron J is recursively determined. If it is a hidden neural network, what we have seen so far is for the output neural network, is for the output layer neurons. And if it is being inside in the hidden neurons, if J is considered in the hidden neurons, how it is computed? The local gradient for neuron J is recursively determined in terms of the local gradients of all neurons to which neuron J is directly connected. For example, if you can see, if we consider this is J, there are some other neurons, but we considering this as our J neuron, and it is being in a hidden layer just before the output layer, considering just before it is in the output layer. So it is directly connected with three nodes. It is directly connected with three nodes. So these three nodes will help to determine the local gradient of this node. If we consider J as this and it is directly connected with 2, then these two nodes will help us to recursively compute this jth neuron's local gradient. Okay, so that's what is said. The local gradient of neuron J, if it is in a hidden neuron, is recursively determined in terms of the local gradients of all neurons to which neuron J is directly connected. So if we consider delta J, it can be computed with the help of function, that is, if we consider this is K1, K2 and K3. So first J, if we consider it is J1 and J2, so J1 can connect with delta of K1, delta of K2 and delta of K3. So after computing the delta K1, delta K2, delta K3, the result will be recursively feedback to delta J1, and then delta J1 can be computed. Similar goes for if it is moved to the layer to layer. If there is another layer of P1, if P1 is connected with J1, J0, J2, then delta of P1 will be considered as a function of delta of J0, delta of J1 and delta of J2, whereas function F2, we are just raising the functions, so there will be no dispute. This J0 will have some function F1 of delta K. Suppose J0 is only connected with delta K1, so here and another function will be considered as delta J1. We have already computed delta K1, delta K2, delta K3, and if we move forward, the functions are as well. So there will be a recursive function that will help to continue or to calculate the delta P1, the local computing error for the local gradients. So I guess we will see this computation a little bit further and more detail by considering this picture. There are two neurons. We are considering J as a hidden neuron and K as our normal output neuron. So as usual, we know the output neurons delta K will be considered as EK multiplied there VK, right? This has been considered. VK is the transfer function of incoming function of K. Okay, so what will be considered as delta J? That is our question of thought. That is our next phase of learning, I guess. So far I think so far we are actually clarified that if we want to compute something in global position, then the nodes will be helping us for computing the error. So if we try to conclude the session, so we will be learning the hidden layer concept and in further classes as well. So far this is the main fundamental process that we actually required, where we learn the output neurons portion today, and we will be looking how this delta J of hidden layer can be computed in the next chapter or next phase. And we already know that this can be done, or this can be calculated through the help of recursive function of the previous layers. So it is being depicted that this will be a function of k or something. So we will be looking for this, and we will be computing this type of neurons in the next phase, how this will be computed. So thank you so far for your patience, and please ask any questions if you want. Thank you very much.